Thank you. And John Mccoy, Hacking.NET Applications, the Black Arts, version 3. I've given this kind of track talk a few times, and I'm going a little deeper into, instead of just showing you the high-level stuff, I'm going to try and drill in and execute some of it a little more directly so you can see it and see that it's easy in the real world. And like I said, he said, I'm Digital Bodyguard, and all of these tools are free up on my website, and all of this tech, research, tools, white papers, videos are all up there to follow along, and it's open and public and free. I'll be looking at attacking .NET applications, the basic tools and methodologies, and it's a little different than attacking a web app. It's a little different than attacking a C++ buffer overflow. It's a different paradigm. And specifically in the tools and research, and what does it take to overcome security inside of an application? What does it take to overcome security in an enterprise that's using that application is kind of where this all goes. And hopefully you'll see that reverse engineering, making cracks, keygens, overcoming security is easy. I attack in memory and on disk. I make tools for reverse engineering, editing executables and DLLs and caches. I make tools for penetrating a process memory space and changing its object flow. In this speech, I'm going to be talking more on the attacking disk side. You can check out the rest of my research if you want to go into on memory. But it all boils down to kind of a simple flow. You attack the logic and decompile it. You infect the logic and you drop your own shims in there. You hook the logic, you get in that flow, you get into that unit test driven cycle. And attacking in memory is pretty much a simple flow of you inject into the target application's memory space, you navigate the structure, and you edit and control that structure. So it's kind of the same and kind of different. Whether you're attacking in memory or on disk, it's all just commands, right? On disk, it's commands, in memory, it's commands. We can't hide these commands from the user. We can't hide these commands from the end processor because they have to be there. And you have total control. There's nothing stopping you from editing memory or commands or anything else inside of your own box. When you're admin, you're admin. There is no higher state. They can't hide from you. And how do you get there? How do you get from a program that's locking you out, denying you something, to bypassing right through that? And that's where you get to controlling what you need. I'm going to be talking specifically about editing on disk. What does it really take to get in there, get your hands dirty, and just take control? And let's look at what we can do with this. That this is what I generally produce. It's a crack you download off the internet, and let's bring up, I'm using 2 monitors, whereas normally I use 1, so I can see what you see. But this is going to be a little interesting. So here's PowerShell, the basic command prompt, and let's install a exploit. This takes over and injects into our Windows, and that infects a machine. And this is PowerShell infected. Let's see, install it, okay. This is going to be a little weird with me switching screens. So this is PowerShell infected, and it still works. And I'm just intercepting that one part, the display function. And this is trivial. This is a hardened core application inside of it where if you shim this and you jack someone's box and you take this over, you're God. You're above admin. You're above the admin using the box. You now control the world there inside. And hopefully by the end of the speech, this will look fairly trivial, that I can demystify going from this payload you download off the internet to how do you produce it, how do you do it by hand, what does the life cycle look like? Hopefully this all looks pretty easy. And it has a defensive quality too. When you talk about your enterprise uses software, how do you know? How do you know what that software does? How do you know if the crypto is good? How do you know if your communication channel is secure? What is it sending home? Now you can reach in there, and with these tools that I'll be showing you, you can take control of an application for good or bad purposes. And that takes us to looking at, this is just a random piece of malware off the internet. Like whether it's something your enterprise needs or requires, how do you look at it? How do you know what it is? This is Gray Wolf. You can drag and drop it in there, and it shows you the proper namespaces and all of that. This is not really different in C++ or Cobalt or even assembly code. All the commands are still there, always. And I made this tool for not decompiling, but editing executables in DLLs. So I have a find main, because I like to jump to the main. I like to see where the program flow starts. That's where I commonly start off from. And you get source code back. You get the names of the classes. And that's what this piece of software does, right? So now we can look through it and understand it. We can know for a fact whether it's doing crypto good, crypto bad. And one side is C#, the other side is IL. This is an IL editor because whether you're attacking VB, C#, obfuscated code, I like to attack it in IL. And so you can do basic, like this has an if up here, and this is an IL editor. You open it up, and you flip this to put a not in front of it. And then you click save, and it saves out an executable. You don't save out code and then compile. That's where you get in trouble. You just edit that one bit deep inside, and you're done. You changed a 0 to a 1 in that key point, and you've subverted a check. And it is that easy. I try and take care of all of the security features you're going to fall up against. And so you could have someone's workstation, and you find this erroneous piece of software called tweakme.exe. And now you can say, well, this is what it does. This is why someone would have put it there. This is what the ramifications are. And you can write a report. You can take that black box assessment and turn it into a crystal box assessment just with a drag and drop. And that's what I'm trying to bring you, that these previously hard things to do or expensive tools to gain access to, I'm trying to bring this to market for free, cheap, and easy, lowering the bar from a skilled programmer to someone that knows how to do scripting and use a command prompt. And that's where this is a more vicious type of malware. I want to show you what I kind of do when I get a contract to do an analysis of a piece of malware, what I actually start out as. So this is the malware unprotected. So this is the malware unprotected. I went through and executed deobfuscation, and Gray Wolf does deobfuscation and all that. And when you open it up, it's gone through and removed the proper naming. But it still has the core structure. It still has the core execution, the core commands. And it's like reading through an intern's code. It's not incredibly hard, it's just painful. And this is obfuscation. And this is what good defensive software, in a weird way, malware, is some of the best installing agents I have ever seen from anyone. It will take care of dependencies. It will take care of collision DLLs. It handles all of this stuff without userless interaction or calling IT. It installs itself. And the same way that it does sanity checks to see if someone has compromised it. It will come in and get the current executing assembly. It'll get the public key. Let's zoom this up. This is getting the public key of the execution to see who am I who I think I am? And we should be doing this for our normal software, but typically this is only seen on malware that wants to make sure it's not being compromised, it's not being sandboxed, it is running in the proper context. And this is where reverse engineering kind of meets rubber and road, where I dig into this and I say, okay, what is it? Well, there's an initialization vector and a key in this one. And why? What is it doing? And it's creating a decryptor. And I just kind of keep reading through and seeing this is a constructor. What are they looking for? They're looking for what assemblies are there? Am I under this assembly? Am I under this assembly? If I'm this one, then I'll use this function. If I'm that one, I'll use that function. And this is strong redundant code. Like a good coder in a good product would do this, but usually doesn't. But malware authors, this is typical. This is what I see normally. And aside from what this really does, This is kind of the day-to-day. You get a piece of malware and you start understanding who made it, why they made it, what the context of it was. And you get a sense of who they are and what they cared about. And it's actually quite a fun process. And whether this is a Microsoft application or a piece of malware you found on the street or in your enterprise floating around. And that's where we come to attacking. We're looking at getting into that application. We want to connect and open its code base. We want to decompile it and understand what the technology was. Are they using AES? Are they using RSA? Are they using GPG? What are they using? We want to infect it. We want to infect it in the way of, we want to change it. We want to make that modification that we care about, right? And take advantage of it. Take advantage of that one point. Do we want to get past a validation check? Do we want to upgrade the security that's failing inside of our enterprise and making us not PCI compliant? Whatever we care about, we can take advantage and implement that change. And we can remold it. Whatever our goal is, we can accomplish that with these tools. And so let's look at that. Let's look at Microsoft Media Center real quick. This is a ubiquitous application, core to Windows. It's protected with all their standard things. And this is their pin check. There's a parental lockout to lock it down. And this is it. This is unfortunately, a fairly typical pin check where you come in, you pass in a string, and that string is checked for null. It's checked for length is greater than 0. And then for no apparent reason, there's an if. There's an if branch depending on what the 0th character in your password is, which if you're a pen tester, you'll never understand this. But if you're in code, it's like, oh, does it begin with a colon? And if it begins with a colon or not, it comes to a different conclusion on how it should validate your pin. And that's an interesting workaround where there's an entirely different logic flow depending on what your stored password is. And it can be nice for understanding the security. So I just kind of need to give you a quick knowledge dump for things that I'm going to use later, but the GAC, the Global Assembly Cache. All .NET things are JITted into the GAC, and the GAC looks like this, but there's a desktop.ini inside that file folder that denies you access. You delete that desktop.ini and it looks like this. And this is your GAC. This is GAC pure, GAC 32, 64, and MSIL. MSIL is the ubiquitous language that can go to any platform. And depending on what you're compiled under, you'll go into different GACs for different reasons. There's native images where DLL is pre-cached and pre-computed and processed into the native image directories. There's multiple GACs at a high level that's in Windows Assembly, Windows SXS, Windows Microsoft.NET, and you go into these different GACs for different reasons. Anyways, back to the demo. But I'm going to be attacking these different core things, and we want to kind of follow along and understand what are we looking at when we talk about attacking it. So here is the same basic attack that we did before. I can open this up, and this attack, I did a password protection down here, and let's dig into it real quick, just to get kind of a sense of how you could take this payload that I have up there as a general attack against Media Center and decompile it, understand it, and do it yourself. That we have a basic form, and it's properly named. You can, let's see, this is going to be a little weird since I'm on your side, but so we're going to look at an unpacker. Okay, so I'm doing decryption, and I'm taking in buffers, and where you can follow where the strings come from, and where am I getting the key, and the key has to be stored in there. And I have encryption functions, and this is normal. In the program you download, the encryption function never gets used, but when I built it, I used the encryption to pack into itself. So it has its own packing logic kind of vestigially in it. And you'll find things that are vestigial from the production or the testing harness inside of it. And you can kind of understand my paradigm, like where does, let's see. You can see I write a file out to disk. And what files, what am I testing for? Like, what did I have to account for in your system to get this payload in there? And so you can easily read through this and understand how I executed this whole payload. And this payload basically gives us the ability to, okay, we'll inject into it and give us the ability to bypass the core password inside of it. We'll run this as an adminner. And, oh, I have it on this screen. Okay. So we have Media Center booting up. Will have to keep switching back and forth. So it'll be a little jumpy, and I apologize for that. So Media Center is a core protected Windows application. And you could put a rootkit in here, you could do whatever you want. We're attacking this parental control. And whether or not we know the password, we've hacked in here, and now any password will work. And that was a quick rootkit, just like the PowerShell. It magically happened, right? But how do we actually execute this? That's what I want to show you guys. I want to take you from the ground up of the beginning implementation all the way through. So I hope you're actually interested in how to carry out these exploits, because that's what I'm going to be showing you. So what does it look like that when we go after it, okay, there I am. So we have a logic in the check pin that we go in and we put a return true, and that's it. Now we're authenticating all passwords. That's nice and easy to understand. But what does it take to actually do this, to actually run from the beginning to the end of this attack? That when we talk about here's a payload that magically attacks them, what are we talking about? So let's take that for a spin. This is the core execution of the attack. That we come in here, we come to Windows, Assembly, and this is what it looks like. It's that protected one. This may actually have a glitch since it caches it, but I have a quick unlocker, but it gets cached. We'll see if this works. Oh. Okay, we can go in it a different way. We'll go in through Command, and we'll go to Windows, Assembly. We'll go to the GAC, MSIO. We'll go to shell, and this is what we have inside of there. And this is inside of the GAC, this is where we're going to. So we'll go inside of here, and this is our target. We have an shell. And so let's do a copy *2c:1. Okay, so now we have our target out here. So now what does it take to actually crawl inside of this and break it? We'll pop open Gray Wolf and crawl inside of shell. And this is actually a full executable that they just redeemed a DLL and started using it. That's not really important, but interesting. Come into Media Center and tunnel down to Options and down to Control pin and check for pin. And so I told you about that logic, that this is the basic logic. This is the IL that's powering the basic logic, and this is the code. So I actually have the cracked version in here right now, so I can set it back by hand. So remove these lines, and let's see, what else is there? Yeah, this one too, that's me. And we have a return true in there, this one. Okay, how about if I have the payload set it back real quick? Nope. Done. Done. Media center, open up the payload, reset to the original, and okay, I have a backup copy on here, just in case I messed up the DLL. Okay, so I'm gonna use the reverted copy that I made by hand. Okay, so here's the pure one that was before I injected it. So options, and parental controls, pin, check pin. And we'll turn off show IL. Ooh. Okay, so this is the basic check that I showed you. I actually have a compromised one in here. Okay, anyways, this is what I typically do. We have this pin, and I want it out. I want to compromise this with a new compromisation. Here is the pin that we actually rip out of the system to validate whether we're there. I can come in here and start adding new lines. So I clear a bit of room for myself to add new code, and I call a duplicate. And down here, I say this is what this IL does. So kind of like assembly code, I'll duplicate the top layer on the stack. So I have the pin, I make a copy of it. I'll put a call out, and I'll put a target. And this target is to a locally reference. So how do we make a target in IL? This is how I showed you, or this is how my program targets DLLs. This is the program itself, and these are all the associated imported DLLs that the program has to call upon. And I like to import new DLLs inside of other people's applications. So this one happens to be having a weird UI, and I want to use a standard Windows call. So I want to use system Windows assembly. Okay, so the cache cleared in the GAC, it's a weird thing. But this is the GAC, again, that I looked at, that you couldn't see that I had to go through command prompt. Anyways, this is GAC MSIL, right? GAC MSIL has system Windows forms. And so this is the system Windows forms DLL inside of the GAC. Instead of referencing it in Visual Studios for the system, this is it right here. We can drag and drop this onto here, and now we have it down here. And so I've imported an external DLL into my target that I can now reference. We have system Windows forms, message box, show, and now I can show out the password. And this returns a dialog result onto the stack, so I put a pop on there. And so that's duplicating a variable, showing it out, and let's save that in here. We'll take this back up to EH shell, which is our target. We'll come here to one EH shell edit that we just did. Drag and drop this into our target. And so this is the actual DLL inside of the GAC that it references. So I'll replace it with this edit. And I didn't really show you, but part of this is also taking out the native image that is pre-compiled. And I go in and just delete it, and then it stops caching it. But, okay. That aired out. I had a pre-canned one that hopefully will kick over. I'm trying to tempt the demo gods with a live coding, and we'll see how it goes. So we have our basic implementation and general parental controls, and okay, I'll execute the same crack real quick on this DLL. So open it up, go to Microsoft Media Center options, parental pen check. Oh, option Microsoft Media Center. I don't see options in there. Oh, Media Center. Okay. Options. Rental. Pen check. And check for pen. Okay, we'll add those 3 lines in. Duplicate. Call. Target operation. Drag and drop the target of system, Windows, forms. I hope this works for all the time that I'm sucking up from you guys, but so on the day-to-day basis, I normally work inside of applications that have this included. And so it's more testing payloads or something like that that I'll drop in. And I just get a lot of questions online of how do I execute this attack that I saw. So now we have this one pre-canned. And system Windows forms, EHL. EHL. And hopefully Media Center. Yes, okay. So come in here and parental control. We show message box. Well, okay. I should have shown a message box. Okay. I'll pretend like I showed you a message box, and then I went through and had that message box copy the hash code out from the pen and put it in the clipboard. So what does this get us, that we're able to reach into the application and retrieve this sensitive data? That now we can go from having an attack that will be able to reach us in and gain access to a core, okay, that will be able to reach us in and get us access to this core logic. That now we're able to access key vulnerable spots. We want to flip a check. We want to be able to set a value to true and all that. That now when we have a media center that is somewhat defended, that now we can reach in and access that core logic. That now whether it's a phone home and validation, that now we can access the core logic of it. And we can cut the logic, we can return true, we can access core values, which if I was able to show you the pin, then I would have been able to do that. But we're also able to execute more advanced attacks that are fairly simple, that we can say we want to retrieve the MD5. And this is the MD5 that it was checking. So now we can take this MD5 validation, and we could come down here to, I'll switch you back to code so you guys can see it. So, so now this is the MD5 validation. It's doing MD5, and they've added a little bit of crap at the beginning, which is good, right? And now you can use this to go and brute force that pin that I brought back. And so you can pull out their logic for validation, reverse engineer it, and make a brute forcer in a matter of seconds, because the code to execute this right here and get this out is a couple of lines of code. The validation check is a couple of lines of code, and then to write a for statement that iterates through, you can obviously see that it could turn around in a matter of seconds. And so you can take this payload here that returns it, open it up, and see how I got that MD5 hash out. That now in form, let's see, it's probably MD5. Here's how I reached in to get that MD5. I used a binding get type to get the DLL. This basically references into it, and I get the parental control. I get the parental control object, and I start doing some reflection to use its own logic to return the value to me. So I don't try and brute force it myself. I use its logic to get the pinned value. And this is how I do it. This is that MD5 return that's right here. And I can change the password or access it. And you can see how I do it. And now you can see how putting a registered equals false can quickly become registered equals true. Or password validation, does A equal B? Well, does now A not equal B? And so you can quickly apply this to is registered and put return true at the top, is a valid key. And you can go so far as to put a tiny backdoor that would be undetectable to AV where SQL cleaning is just returned. And now you've bypassed SQL cleaning inside of an application. And so now when you pop a box and you're admin on the box, what do? Well, you put this in there, SQL cleaning, on that web server, and you've turned off SQL cleaning. And no one will necessarily find it because it's in a compiled DLL. And if they did a whole diff of the system and were whitelisting, that they might see it and they might understand it, but good luck, and you're certainly past AV on a high level. And so now this seemingly hardcore attack, you might find this and say, wow, someone had some real skill. And as you saw, it takes a couple of clicks, and it could be a high schooler that barely understands how to code. And that's what I'm trying to bring back, is that this stuff that seemed very complex is now show me the key out. And it's highly life cycle and actually maintainable from a I guess a high level perspective that someone can easily understand. How you now pass in your username to do a validation, and you do some math and arithmetic, and this is 90% of what I see, that you take in the code that came in with the username, and if it fails, then they don't validate. And that to do a replay attack is now simple, that you can now rip out that value that was necessary and just simply play it again. And that's bypassing a key check. That's registering software. And for some bad software, that's even registering your validation to execute certain commands or authority rights in the enterprise. And this is typically what I see. You'll see a public and private key protection. This is on the people that are doing updating for their software. This is probably 80% of the people that are doing it well. They do a public-private key. You change the key. You change where it goes to, where it phones home to, and now you have software inside of an enterprise that is now keyed to you and coming to you. And at any point, you can push an update. There's a random amount of math, and then you just have to find a couple of key variables, and that's the secret. There's a server call. You simply repoint it, or you hack that server call in some fundamental way. Setting a value can bypass all sorts of security simply, and complex math for key validation is the other part. And 1% of the time, they actually ship the key validation to you. And why beat them when you can join them? You don't need to. You can just simply replace it with a key that you like, that's easy. You don't have to spend a lot of time or effort. And so what does it take? What does it take to really attack an application? And this is the best keylogger. It is a piece of software that I've been wrecking for the last few years. And by the end of this, hopefully you'll see why. It's a keylogger that sits on your system, and it's obfuscated. This is a protected application. It is the standard obfuscation. You can scroll down here and see that it's from Dofuscator, and there's a signature. You now know what it was obfuscated by. You can go and Google it to see what security they have in place. Do you need to worry about it? Do you need to bypass it, or can you ignore it? And it just so happens that validation I want to go after is in here. And so this is why I attacked this application viciously. For many years, I just wrecked this application because it does a password validation, and that's it right there. It takes in what the user typed in and trims it. It takes in the stored password and compares them. No crypto, no hashing, no protection. Your password is stored in the clear. And for a piece of software that wants to pretend to be some level of security, that's horrific. Like when they stop storing it in the clear, I'll stop attacking them. And so this is the simple case where here is a branch on false. That's what it says down here. And I try and make it nice and easy where you take this branch on false, turn it to a branch on true, and now we've added a not. And so now not password validates. We click save it out, and now we have this one that, yes. So any password now validates. Oh. Ooh. Okay. I'll pop that through one more time. Let's see. Did I save it out correctly? Let's see. Best keylogger. Open. Let's see. This was at. Oh. My demos are wrecking. Ooh. Okay, that's okay. Keep moving. Okay, so this password. Here's where we get a password right here. I'll add a couple of things, just like I did before. I'll call a duplicate on here, a dupe. We'll call it callout, just like we did for the first one. Target it to Windows System Forms, System Windows Forms, message box show. We'll add one more pop to clean it up. Save that out. Okay, let's take that for a spin. So type in, I have some sandboxes that I'll try and clean real quick. Ooh. Okay. Well, okay, so assuming that this worked, I would take the password in, I would show it out to the user, and then I would subvert the check. For some reason, that doesn't seem to be executing. And something interesting to note is that on a successful password validation, this is a logic that gets executed. You change one variable, and then you execute OK dialog result. And so you could attack it, or you could inject into memory and execute these two lines of code and be able to bypass that. And so when you actually get in there, that attacking in memory is so much easier. That you're talking about these two lines instead of reverse engineering and trying to, you just inject in and attack it. And I have going in there with Metasploit or these other payload systems. And I have a standard payload system that works off of Windows DLL injection. And I won't really have time to introduce it, but it's called Gray Dragon, and it's up on my website with payloads and pre-canned. And so why don't they hash it? Why don't they protect the password? Is kind of where I'm going with all of this. That if they're gonna claim to be secure software, whether this is Norton, Symantec, or off the shelf, you don't care, you're using it inside of your enterprise. And now you can reach in there, look at it and say, hey, we don't want to use your software until or unless, or maybe you have to use it and you'll patch it yourself. And now you can quickly patch it. And so if they would just use SHA-256, do a little bit of salting, I would stop attacking them. And for multiple years, they've refused to, they've done plenty of upgrades to try and stop me in different ways, and that's all they have to do to stop me. That I'm a highly skilled reverse engineer spending hours attacking them, and there's no level they can get to that I can't get higher than. And there's nothing that will stop me except for putting a SHA-256 on the user password. And so when you talk about why is this hacker attacking us, this is why I'm attacking them. And so it's not necessarily apparent why someone would attack your software. And I'll try this real quick. It will probably end poorly, but I'll try and attack this software one more time. So let's open up Gray Wolf, and let's drop in the same piece of software. Let's drop this in here, and let's go after it. So now the target is going and breaking the validation of the software. Let's open it up and make sure that we can access it. Okay, I reset the software. I'll put in password 1, 2, 3, 4, 5, 6, and access the software. Okay, so this is it. We come in here and we have our license. And so how do we attack this, right? It's an obfuscated piece of software. I know this unlock button goes to code. How do I get there, right? And this is where, well, since I messed up a couple of the other demos, I'll just do a memory demo for you real quick. So what does it take? What does it take to break into this application? So I have Gray Dragon targeted for all the different frameworks. You take Gray Dragon, you target this, it finds 32-bit, it uses a 32-bit compatible payload, drops this in there, and now we have a shim that will load any DLL executable, and it'll run void main inside of the executable. So I can drag in an executable, and now I can edit the application. I've injected into its application. And that's a couple of lines of code, less than 50 lines of code for this entire payload that does core editing. And I can do all sorts of crazy stuff. But this ask button, now it added a right click to everything on here. I can right click this, and this is what that button fires, right? That's the unlock code. The unlock code says, okay, well, I want BAZ, I'm this function, class B, function A. So let's go look at BAZ, right? That unlock button goes right there. So now when we come in here, we can be like, oh, well, let's go to B. And so a good programmer would put all of the logic in that one class, right? So if that function fires into there, then probably the rest of the logic is in there. So let's see, BAZ. And so yeah, sure enough, that's it. And so that's going from blind in an application, memory injecting, finding out where a button goes, going to where it goes, and now we see this activation failed, activation succeeded. And that's kind of the round trip, that now something that was protected, that they spent time to protect, we can now subvert it quickly and be able to bypass core functionality. And so you read through all of these functions in here, and it turns out that it resolves one function to another, and this eventually resolves to BAA. And so, as I said, a good programmer would put all of the core logic in this area, so it resolves to BAA. And so here's our activation string. This is where the activation actually executes. That now we have a service call out to the internet, and it takes a certain action. And it will probably blow up, but let's look at attacking that. Let's look at attacking this action in here. That now we scroll down and we find here is the best keyloggers web reference activate key call. So it calls out to the web. Okay, well, let's delete that line. Okay, well now it no longer calls out to the web. It just doesn't do that call anymore. And that's what we're going for, right? We're going for that quick, get me in there and let's attack it. And let's see, Let's see. And there should be probably one of these two. Let's see. My notes are for some reason off, but let's flip this one. Okay. We put a not here. Let's see. 1, 4. Yeah. Okay. Probably this one. Okay. We'll try this one. And let's go and attack the login logic real quick, just one more time to see if we can bypass that. So WAW, and then I think it was AWAD. Okay, here's our logic. We'll flip this check to be a true, and let's show out the message box real quick. Chance it'll work. Get one of these going for you. Duplicate, call, target, system Windows forms, message box, show, pop off the returned value, and save it out. And so we have a hacked compilation of this that has a chance, judging from how this has been. So we'll take this one. Okay. I'm not sure where I'm messing up. So let's see. This really does work in the wild. Okay. My demos are all to hell today. So ta-da would work, but totally doesn't today because the demo gods hate me. But that would be breaking their core security for validating these two different critical sections. And that's where I live. I live down in IL. I actually live where IL becomes assembly code and where the framework does memory management. And I live in that area of .NET that you never consider. And that's why I can find exploits so easy, because I live in an area that you don't know exists. That now I can infect you in the GAC, and you're whitelisting in program files, and everything whitelists just fine. And so now in your forensics investigation, you forgot to check the GAC, and that's where I'm living. And so when you talk about this level of skill, like, can I bypass someone with less skill than me? Yeah, I probably can. Can I get past someone with more skill? Probably not. And when we look at an application, like, we have security dongles, we have all of this phone home ability, and we'll throw on crypto. And this is where I like to attack you. I like to attack putting backdoors in your update logic, in your phone home. If you're doing encrypted communications home, I can now piggyback, repoint that to my server, get encrypted communications that you're allowing to come out of your network, and exfiltrate a couple of records every single day. And when you have a security dongle, I can now add my dongles to your sequence. I can now validate myself into your system. Or your crypto. How do you know if your random numbers are random? I can now go in, just like the NSA, and cripple you in some fundamental way that I'll still pass all entropy checks, but I will have the keys to your kingdom. And there's no way that AV is going to find me. And that's what I'm trying to bring, that we consider applications to be this secure, unfathomably hard area to attack. And it's not. It's really not that hard, that this is just a level of skill that was held back from us because the tools were expensive, that you were talking about IDA Pro and thousands of dollars, and now it's simply code obfuscation that you have to get past. You have to read through a little bit of challenging stuff. And when it comes down to it, it doesn't stop anything, because this is obfuscation, that you're talking about, oh, this is a value that comes back, and you just have to read it or just put in something that shows you out the code. But they put in security, right? Microsoft gave you security. And yeah, .NET does have more security than C++ and the previous languages. It gives you code signing and 1024-bit crypto, and you can bake this into your enterprise and all that. And this shuts down tampering because there's no way that they can get this strong name, public signing key. It's so strong and will protect you. And this is a public key, and it's a public key signed token, and it's actually pretty strong. And at the end of the day, it identifies the author of this public key. And well, unfortunately, no, it really doesn't work. And they tell you that it's going to defend you, right? Well, why? Why would I say no, right? That you've gone from a protected to an unprotected state, and you don't understand why. And that's where experts like us come in, that we can now say, well, your application that you thought was secure is completely overrun with hackers, and you don't even understand that it is, or why, or how. And that's because you take an executable and you have a mal executable, and what's the difference? It's that public key that's protecting it, right? Well, when it comes down to it, this public key can be transferred. This public key that's public-private 1024-bit crypto is simply transferred, but broken, right? Because it no longer hashes. And that's where the entire vulnerability and easy bypass that I found came in, is that when you talk about this attack vector, it's off by default. Windows doesn't go through and hash every DLL. When you're loading a video game that's 2 gigabytes, it doesn't hash 2 gigabytes, it checks the keys. And I transfer the keys over. And so I'm using correct keys on mal software. And that was 2 lines of code for me to implement. That this entire system is subverted with a couple of lines of code. And Grey Wolf does that automatically for you. That's why I can edit these core applications inside of Windows and bypass all of their security signing. And that's what I'm trying to bring to you, that you can look at these different things and we can actually start securing this, that when you talk about a whitelisting application, if you find an executable or a DLL with a key that's mismatched and the DLL has been infected and erroneously re-signed, that's an indicator. But how many of your tools would find that? And that's why I'm putting out all of this research, to try and move us forward and not just become complacent, and trust. And so if anyone does care, there's a registry entry that you can turn it from default off to default on, but it'll slow your boot time down. And if a hacker gets in there, they could flip it. And that's a choice. That's a choice that we can make, that Microsoft documented but doesn't tell anyone about. And it will cause an error in the DLL. But if you put it in the executable, it will still say, oh, well, the certificate probably expired, so load the executable anyways. It's a mal-signed, non-validating certificate. And it'll still load. And so you can set that at the enterprise, on and on. And that's why understanding the GAC and all of that is so important, that when you load a DLL, it goes into the GAC turns out, and your native image is destroyed, and it has that whole life cycle that I showed you. And now you have malware propagating through your enterprise. And so you can infect the framework the same way, and you can load assembly code the same way, and put shims in, and it's easy. It's easy to do this. And so that's where my skill sets of application layer logic, defendable applications, function level logic, and application security reviews comes in. And so think about function level security, layered security, defend your application, defend your APIs, and armor any application, whether it's yours or someone else's. So that's where I'm going with all of this. And I hope that it speaks to you and you appreciate that this is all easy, and all of my tools are free, will remain free, and it's open and should be usable by any low-level developer or someone without development logic. So thank you very much, and I hope you enjoy the tools.